Hello. In this video, we're going to take a look at the issue of statistical error bars and how they are calculated and interpreted in particular. Let's start with a relatively simple but profound observation about real numbers. Numbers are abstract mathematical objects, and usually, when we deal with symbols that represent numbers, we usually intend a precise value for the number. So for instance, pi, the circle constant, has a particular value. It is equal to the circumference of any circle divided by 2 times that circle's radius. Now think about the decimal numbers that we normally deal with. Decimals provide an imprecise representation of these precise numbers. So for instance, pi here is shown terminated after the 11th decimal place. In other words, the number shown here is not the true precise value of pi. It is only an approximation to this number. What we should really do, then, is indicate how close this imprecise value of pi, how much this imprecise value of pi might differ from the true value. We can think about this business of errors and imprecisions in our estimates of numbers in a different way. How, after all, do we get the numbers that we put into mathematics and physics models? We take measurements. Any measuring tool is a blunt instrument that can only measure things to a certain accuracy. The ruler shown here, for instance, allows us to measure this rectangle in terms of the number of centimetres and millimetres. But this gives us a measurement of limited accuracy. We might try to estimate to the nearest 0.1 of a millimetre by guessing where we are between the two lines, but it's important to remember that this is an estimate. Thus, when we quote the measurement we made using the ruler, we should quote a number and an associated error bar. In this case, an error bar of 0.05 centimetres indicates that our ruler is only accurate enough to measure things to the nearest millimetre. This business of considering errors and imprecisions in our measurements is also important when we perform calculations. For instance, let's suppose that we want to measure the area of the blue rectangle shown here. We can measure the length and height to the nearest millimetre using the ruler from the previous slide as shown here. Notice that once again we have error bars on these two numbers, and we should consider these error bars when we perform the multiplications required to get the area. We should thus predict that the true area of the shape lies within a certain numerical range. The lower bound on this range will be 5.2 times 1.7, which is 8.84. The upper bound, meanwhile, will be 5.3 times 1.8, which is 9.54. We cannot really be more accurate than this in our predictions, however, because there is an inherent inaccuracy in our measurements. Every tool we have for measuring things is a blunt instrument that will only measure the universe with a finite precision. It will not measure the universe with infinite precision. Having got to this stage, you are possibly wondering what all this has to do with statistics. Well, in answer to your question, statistics as a field of study started with governments trying to monitor the income of citizens. This is important, as one can only determine how much tax it is fair to take from the citizens if you know how much your citizens earn. If you try to take too much money in tax, the citizens will probably revolt. At the same time, it is important for the government to know how much money they will be able to take in terms of balancing the budget and deciding how much money they can spend on wars, weapons, and public services. In fact, it is important for the government, if you're the government, you want to know how much money you would expect to take in tax, just so as to ensure that the tax collectors don't steal from the exchequer. So let's now suppose that you are the government and you need to determine how much money you're going to take in tax in a given year. What can you do? Well, the most naive thing you could try is to go out and ask everyone how much money they earn. This would give you the exact amount of tax you would expect to collect. The problem with this approach, however, is that there are a lot of people to ask. In fact, asking everyone is a task that resembles the painting of the Fourth Bridge, as people are constantly born, they move to new jobs, they die, and they get promotions. Thus, by the time you've asked everyone about how much they earn, the information you will have got is obsolete, as some people will have changed jobs, some people will have been born, and some people will have sadly died. The only thing that you can thus feasibly do is ask a subset of the population. In this figure, let's suppose that the red arrows point out the people that we've asked. The question then is, if you just have information on this subset of people, does that information allow us to deduce anything about the income of the crowd? Clearly, asking a subset of individuals about what they earn is a very blunt instrument for determining the incomes of the people in the crowd. We should thus find some way to say something about the error bars associated with this measurement. Let's make this notion more precise. In the first equation shown here, the sum runs over all the people in the crowd, n of t, and Si is the income of the ith person in the crowd. The quantity mu, calculated by this equation, is thus the mean income for the people in the crowd. The second sum, by contrast, runs over the subset of people that have arrows pointing at them. These are the people in the sample. There are ns, which is less than n of t of these people, and Si represents the income of the ith person in the sample. Mu s is thus the mean income for the people in the sample. Now the question becomes, can we approximate mu, the true average income, as mu s, the average income of our sample? If we can do this, then it would obviously make the government's life much easier, as they can get an idea of their expected tax take by only asking a subset of the population. The answer that the early statisticians found to this problem involved using ideas from probability theory, which had been developed separately by thinking about games of chance. Incidentally, the fact that these two fields developed separately is, in my view, rather unfortunate, as probability theory and statistics make very little sense as separate subjects. The fact that they are often still taught separately is baffling, as a student learning statistics without probability theory can only have a shallow, mechanistic understanding of the statistical tools they are being taught. This puts them in great danger of making errors in their analysis. Returning to the point in question, however, the idea that statistics took from probability was the notion of a distribution. A typical distribution is shown here. In the context of the problem of the government determining the income of each person has, the way that the distribution is shown works like this. On the x-axis, we have the possible values for the income of a person. For our problem, this will be the set of all positive real numbers. On the y-axis, we then plot the proportion of people who earn this particular amount of money. Strictly speaking, it is the probability that a person has that income, but probability is a much more slippery and difficult concept to understand than proportion, so we will leave a discussion of that topic to other places. The point of this slide is to show that we now have a way of understanding this process of picking people at random from the crowd. Whenever we pick out a person from the crowd and ask them about their income, we're taking a sample from this distribution. Furthermore, and importantly, we are assuming that this distribution is the same for all the samples that we take. The business of introducing a distribution is very useful, as we can show that the exact value for the mean, the value that we would get by asking everyone in the crowd, is given by the following integral. This quantity is known as the expectation of the distribution. On top of this, we can also get a measure of the spread of income in society by calculating the quantity shown in red here. This is the standard deviation. Best of all, however, is a result known as the central limit theorem. This theorem tells us that if we take a set of independent samples from our distribution, finding a random subset of the crowd about their yearly income, for instance, and if we add all these samples together, we get a random number. However, as long as our distribution for the incomes has a finite mean and variance, the probability distribution function for this random number, Sn over n, will be Gaussian. In other words, this happy theorem tells us that we don't need to know anything about the distribution of incomes in society, as if we take a sufficiently large number of samples, we can think of the distribution of the aggregate mean from all our samples as a Gaussian. This idea is dealt with more in a separate video, which also introduces the notion of constant confidence limit and a method that we thus use for calculating error bars on our estimates of the expectation. For this video, we will note that the expression shown at the bottom of this slide tells us about the cumulative probability distribution function for the random variable Sn over n. This is a nice compact way of stating the central limit theorem, but it's not that helpful for what we want to look at here, largely because the distribution that is calculated by this function is different from the probability density that I introduced on the slide before this one. We can express the central limit theorem by thinking about the probability density function for the random variable S, the sum of our samples, over n, the number of samples, as shown here, however. Furthermore, on this slide you'll also see a plot of this function. The function is peaked around the true mean, mu, which I have set equal to 0 in this figure. Furthermore, the width of the function is related to sigma over the square root of n. This second fact tells us a rather nice new fact about the central limit theorem. As n, the number of samples we take, increases, the distribution for Sn over S over n gets narrower. Consequently, as we increase the number of samples we take, we can have much more certainty in our estimate of the true expectation. Let's thus think about how all this relates to the question that we started off with. If you remember, we had introduced the following equations. We had noticed that in the first equation shown here, the sum runs over all the people in the crowd, n of t, and that Si was the income of the ith person in the crowd. The quantity mu calculated by this equation is thus the true mean income for the people in the crowd. In the language that we have just introduced, we know that this is the true expectation for the distribution of incomes. The second sum, by contrast, ran over the subset of people that we chose to sample. There are ns, which is less than n of t, of these people, and Si represents the income of the ith person in the sample. Mu_s is thus the mean income for the people in the sample. The question we had asked was, can we approximate mu, the true average income, as mu_s, the average income of our sample, and thus make our life much easier? Now that we know about the central limit theorem, we can give an unequivocal yes as our answer to this question. Furthermore, we know that if we make our sample larger, if we increase an s, our estimate, mu_s, will get closer to the true value of mu. There is still a problem, however, when it comes to determining the error bars associated with our estimate of the true expectation mu_s. We need to determine sigma, the standard deviation. Maybe this is not so bad, though. After all, we've just seen that the central limit theorem tells us that we can calculate an approximate value for the integral shown here by calculating a sum of samples from our distribution as shown here. The integral shown on red in the left-hand side here, the integral inside the square root sign, looks very similar to the integral on the right. So we might be tempted to ask if we can determine it by taking a sum of samples from our distribution and adding together the following functions of the samples. There is an obvious problem with this approach, however, namely that we do not know the exact value of the expectation mu. All is not lost, however. Remember, mu in our taxation example is calculated by adding together everyone's income, and although we do not have an exact value for this quantity, we do have an estimate of this quantity that we calculated by adding together the incomes of the people in our sample. The second quantity is what we call a biased estimator for the true expectation. The question that we should thus ask is how much would we expect a biased estimator of the variance, a variance that was calculated using our biased estimator for the expectation, mu_s, in place of the true expectation, how much would we expect this biased estimator to differ from our true estimate of the true expectation? In other words, what value would we expect this expectation to take? Notice that this expectation measures the difference between the true estimate of the variance, that is calculated using mu, and the biased estimator of the variance that is calculated using mu_s. We can determine this expectation by performing a few simple manipulations. First of all, we multiply out the two set of brackets. We then note that the terms in xi squared in the two sums cancel, and that we can take terms that do not depend on the dummy index of the summations outside of the summations. When this is done and the two summations are combined, we thus end up with the relatively simple expression shown here. We next note that we can take the term in brackets outside the sum as it also does not depend on the dummy index. We are then left with the sum of the xi values for the n values in our samples divided by n. We know that this is equal to mu s though by the definition of mu s, and that we can thus rewrite our expression as shown here. Then we multiply out the brackets and cancel terms. We arrive at the following, which is an expression that we can rewrite as mu s minus mu all squared as shown here. This expression is equal to the variance for mu n mu s. In fact, this is another way of writing out the definition of the variance. We know what the variance of mu s is though. Mu s is just the mean for the samples from our distribution as shown here. The central limit theorem tells us that the variance for the mean of n samples is just sigma squared divided by n. The final result that we have arrived at is shown on this slide. The expected difference between the true variance and the biased estimator for the variance is sigma squared divided by n. Let's now simplify this expression down so that we can get an estimate of the true variance sigma squared. If we use the true mean in the first sum here, this first quantity will be equal to the variance. We thus find, when we rearrange this expression, that the quantity that we have calculated by using mu s in place of mu is equal to sigma squared minus sigma squared over n. If we thus rearrange this expression and isolate sigma squared on one side, we find the following expression as the unbiased estimator for the variance. Let's now finish by briefly summarizing what we have covered in this video. We began by noting something that you possibly already knew, namely that we can estimate expectations by adding up random samples from a distribution. In other words, the mean of a collection of samples taken from the same distribution tells us something representative and meaningful about the distribution. In the language of our example, by just collecting the incomes of a sample of the population, we can say something about the total tax revenue the government would be expected to take. What you perhaps didn't know about is that all this is connected to the central limit theorem. This process of taking samples from a distribution and calculating a mean, and thus extracting something about the population, only works because of this theorem. The central limit theorem lies behind much of the statistical analysis that we perform. We also, in this video, discussed error bars and how these allow us to quantify how precise our measuring instruments are. It turned out that the central limit theorem is also useful when it comes to calculating the error bars that determine how close to our estimate of the expectation is to the true value of the expectation. We typically use it to calculate an error bar as follows. We first calculate the variance of the distribution using the formula that we've just derived. The error bar that is then often reported is the square root of sigma squared over n, although wider confidence limits are often used. I hope this video has given you a better appreciation for the mathematics underlying this process of estimating error bars for statistical data, and on how these quantities are calculated and interpreted. This is difficult mathematics, however, and you may like to investigate further by investigating the central limit theorem some more, or by investigating topics such as probability theory. For now, though, thank you for your attention.